And it looks like we're live. Yes, we're live. Hello, everybody. Time for another hangout. This hangout tonight will be a little weird because it will basically be a large, long lesson with Hector regarding the physics of gravity and buoyancy. So a little bit to the background. What happened was that about 2 or 3 weeks ago, Hector was in a hangout with Anthony Riley and a bunch of flat earthers, explaining to them how gravity and how buoyancy work. But Anthony, it looks like Anthony didn't really understand it and made a video about it, completely misunderstanding what Hector said. And today we'll be talking about that. So without further ado, here's Hector.
Hey. All right. So I'm not going to ask you to basically watch the whole hangout. It's very long and kind of chaotic. Basically, the central point made was basically water is supposed to have weight according to gravity, and if we submerge something in water, there's going to be a lot of water above it. And if you take a lot of water, put it in a bucket, and put it on top of your head, that weight is going to push down on your head. So you're going to feel heavier and being pushed down. So why, if we put something in water, isn't it pushed down further by the water that's above it? And in extension, that during the course of the hangout, which turned out to be kind of chaotic for reasons that I maybe could get into at a later point, but they are kind of secondary. At some point in the hangout, the goalpost had moved to the point where we weren't talking about, well, this buoyancy thing anymore, but then it had completely turned to prove to me that gravity is real, which I am going to do at another time, not now. For this time, I'm going to address the point with the weight of the water. Now, what I did was, let's start it this way. I used pressure as a way to explain the behavior of the water all around, either your head or later on an example of a rock was used, because for the water that's not above the rock, pressure is both the easiest and a absolutely fine way of describing that behavior. So I'm first going to go into why that is, how exactly pressure works, and then show that if you calculate your problems with pressure, you basically arrive at the same results where you would without pressure, but you can also apply it generally, not only for water above you. Then I'm going to go into how pressure is called as long as you don't do anything other with the water, like compress it in a piston or something. I'm going to go into why pressure is also caused by the weight of the water itself due to gravity, and how that, if you take into account the pressure from all around your rock, causes the effects we see. And in case you're for whatever reason allergic to pressure, I'm then also going to go into a probably a little bit more complicated, in particular more complicated in a mathematical sense, solution that works without pressure, but it involves derivatives and energy conservation. So I don't know, pick the one you understand better. And well, if after that I'm still not yet tired enough to stop that, we're probably going to go and talk about Anthony's video a little bit. Now, pressure. Pressure is in the world of physics defined as a force over an area. Basically, how strong you press down on something. In that sense, and pressure in itself does not have a certain direction. It's a property of solid, liquid, and gaseous matter. Although for solid matter, it isn't that its effects aren't that obviously visible, mainly because solid matter has a hard time changing its shape. In gaseous matter, pressure also gets kind of interesting because gaseous matter is easier to compress. However, fortunately, for today, we're just going to talk about pressure in water. So in that sense, we don't have to worry about compression that much, because basically water isn't that easily compressed. Still possible, but kind of hard. Now, for the example of the bucket that we got. So basically, we've got our bucket of water. In that case, that water will have a certain weight to it. I'm just calling that the mass m. And if we've got gravity around, that will cause that water to be pulled in the direction of the gravitational field. The gravitational force, F index g, is calculated as a galactic constant times the mass of the first object times the mass of the second object divided by the radius squared in the and it is directed towards the larger body. Now, when we're talking about Earth, then most of the time we are going to use something called the gravitational constant, the lowercase g, which is basically factoring in both g, m1, and r squared, since the gravitational constant isn't really going to change. That's a constant. The mass of the Earth isn't going to change, and the radius is not going to change to a degree large enough for it to really matter. So we can simplify the formula as lowercase g times m2. And in that case, that m2 is going to be the mass of our water, and g is going to be the uppercase G times m1 divided by r absolute squared. In case you don't know what these lines mean, they are in essence giving us the length of the vector, because if we want to be pedantic, that r isn't just a number, it is a so-called vector, which is a number with a direction, and with these two bars, you get rid of the direction. A little bit too much detail, never mind about that. We don't need that for now. So there's a total force that is acting upon that water. That force is arriving here at the bottom plate. So the pressure onto that bottom plate would be the total force, and that's the gravitational force of the water, divided by the area, which would be gravitational constant times mass divided by area. Now, the total force that we get by that would be the pressure times the area. That's how you get the pressure. If we put that into if we add in that formula for the pressure, we get gravitational constant times mass divided by area, multiplied with area, which returns to gravitational force times mass. So both for the standard gravitational force without pressure, as well as the force that is created due to pressure, we get the same results. In that way, pressure caused due to weight of the water is a correct description of the same phenomenon, simply by calculating it in a different way. It's kind of a thing in physics. There are a lot of ways to calculate one thing in a lot of cases. It's just that for most cases, there's one way of calculating it that is, well, either or the way that that makes it the most obvious what's happening there. Now, for water pressure in a certain depth, basically, as you've got more and more water above you, there's going to be more and more weight pushing down on basically that bottom side of the bucket. And if we say basically the bucket is filled to an height h with water, then we can rewrite this. Then we can rewrite this here as pressure equals force over area equals G times m over area. And the mass can also be expressed as density times volume. So gravitational constant times density of the water times the volume of the water divided by the area. That volume can be expressed as the area of the bucket times the height, which yields gravitational constant times density of the water times height times area divided by area. And if you multiply it with area once and divide it by the area once, it cancels out. And as a result, you get gravitational constant times density of the water times height. Now, if we put that, that basically is still the same amount of force as up here, simply calculated in a different way. And this is the point where things start to get interesting. Because as I said, pressure itself doesn't really have a direction. So in the case of our bucket, or I'm just going to draw it anew, there's going to be pressure all over the place. And that is going to be get kind of obvious if, for example, there is a set of holes in the side of your bucket. We've got our water here. And we've got two small holes in here and in here. I hope they'll be visible on the stream. And if not, you'll have to imagine them for a moment. Now, here, this hole is higher than the lower hole. So there's less water above that hole, and therefore there's less pressure here. As I said, the pressure works basically on everything, also the water itself. For the water inside that bucket, that isn't really going to make a lot of difference, because in all due essentiality, the pressure is going to work on to affect every single water molecule in the same with exactly the same strength from every direction possible, which means that all forces will end up canceling each other out, as long as there's basically water in one direction. Now, in the case of the hole in our bucket here, there's water to the left, which has a certain amount of pressure, which is going to press against it from the left. Basically, pressing against here, and also pressing against all other pieces of the bucket wall. However, at those two places, there's no wall of the bucket in the way to keep it from flowing out. Therefore, it's going to flow out. And basically, as the pressure gets stronger, the further you go down, there's less pressure up here than up here, which means that the water down here is not going to be that quick, and the water up here isn't going to be that quick, and the water from the hole down here is going to be a lot quicker. You can test that very easily by just taking an empty pop bottle, just poking two holes in it, and then filling it with water and taking a look at what's going to happen. So this observation very well confirms that calculation over here. Now, in terms of how exact, how very precise that is, and how it applies to every single surface, think about an example like this. You've got your bucket here. You also have water, but now you're pushing an empty cup into that water. So there's no water in that cup. You're going to have pressure affecting, again, every single surface inside that bucket. So basically pressure to left and right here. Now, the bucket itself isn't going to notice a lot of that pressure, because basically the pressure to the left and the pressure to the right are of equal strength, and they're going to cancel each other out because same strength, opposite directions. It's like a tug of war where everyone's exactly as strong. Now, you are also going to have forces applying to those areas, and in all cases perpendicular to those areas. There's going to be a force pushing against the cup that you push into the water from below it, but there's no force from top down to cancel it out. So that cup is going to be pushed back out again. If you make that cup a little bit larger and a little bit longer, you in all due essentiality have a boat, and that boat is going to be pushed upwards until the weight of the boat itself cancels out the force due to the pressure below it. Now, so much for how pressure works. I hope this was as understandable as necessary. Now, we're going to go to the example of the rock. We've got basically our object. In that case, I'm going to draw a very crude object, which has an area A, both at the bottom and at the top, and a certain height to it. And the whole thing is submerged in water. Up here, there's going to be a water pressure, and down here, there's also going to be water pressure below it. Let me draw that again. That's going to be very crowded. So our object with pressure working on it from all sides. Now, if the pressure were all the same on all sides of and on all surfaces over our object, then all the forces of the pressure would cancel each other out. And in the air, basically there's only very, very few pressure difference if we go up higher. So, well, we don't really notice a lot of that. That's why the rock was rather heavy outside of the water before you put it in. Now, as we are in the water, if you notice down here, the weight, or basically the pressure of the water, not the weight, I'm kind of tired, sorry. The pressure of the water is directly dependent on the height of the water above it, or basically the depth. So if there's the surface of our water, this is the depth of the water at the top end of our object, and H1 and H2 is the depth of the water at the bottom end of our object. And basically in here we've got delta H, which is the total height of our object. Then there's going to be a different pressure up here, down here. I call them P1 and P2 so you can tell them apart. Pressure 1 is going to be gravitational constant times the density of the water times H1, and pressure 2 is going to be gravitational constant times density of the water times H2. Now, the forces acting upon our object, which I'll call F1 and F2, are set pressure times the respective area. So F1 is G times rho water times H1 times the area of the top down or bottom up surface area of our object, and it's the same for F2. Gotta push that up a little bit so you can see it. E times V times 2 times A. Now, if we want to know how strong the total force of our water is, we gotta see how, we gotta know the difference between those two forces, because if they're equal, they're going to be canceling each other out. If they're not equal, they're not going to cancel each other out, and there's going to be a force remaining, which is going to be the force that we will measure. So the force for the total forces due to pressure for F index P is going to be G times rho omega times the area times the distance in height. And if you remember correctly, the distance in height is our delta H here. So we arrive at G times density of the water times area times the height of our object. Now, what happened here, and why is that now only dependent on the total height of our object and not how high it is below the water? The reason for that is, if you move your rock or your head or whatever is in the water further down, let's say by 1 meter, then the height at the top of your object is going to increase, or basically the depth below the surface of the water is on top of your head or your object or whatever is going to be increased by 1 meter, and also will the depth at the bottom of whatever object you're submerging right now. And that increase in depth will be cancelled out due to that sum, due to the fact that what creates that total force that you see is the difference between those two forces. And if you increase, or between the two forces increased by, created by those two heights. If you increase both by the same value, the difference between them is going to be the same. And the difference between them is this delta H. Now, the total force of our object in the water is going to be the force that is imposed upon that object due to gravity, Fg, plus the total forces due to pressures, which results in the mass of our object times gravitational constant, plus the forces due to density due to pressure, density of the water times gravitational constant times area times height. Now, area times height, already had that one. That's the volume of our object. And the volume of our object times the density of the water is basically the mass of the water that has been displaced by our object. So, hold on, I'll just write that down right here. Water times volume equals the mass of the water that we've displaced. So, this equation solves for mass of our object times gravitational constant plus the mass of the displaced water times the gravitational constant. And now, let's talk a little bit about the weight, about the scale that you used to measure the weight of your rock. In all due essentiality, how that scale that you used to measure how heavy your rock was, both in the water and in air, basically works by measuring how far the tray of the scale is pushed down. If we want to be, and in that case, I have to be pedantic about that, because what's pushing down the scale, the scale's tray, is not the mass itself, but a force. You can detect that very well by simply holding it sideways and pushing in the scale by your hand. There's no the weight of any weight or force due to gravity will be downwards towards the Earth and not sideways. So what the scale is measuring there is force, and it's going to and it's also going to measure force all the other times that you put something on it. So this here, the mass of our object times is what you measure when you have something in the air, and if you have put it in water, then there's going to be an additional force counteracting that force of gravity. Therefore, the way your scale is going to show a lower value of force. It should be noted that I made a small mistake here. H2 is larger than H1, so if I subtract H2 from H1, I'm going to get a negative value here, minus delta H, which means that Fp is going to be negative. So there's not a plus here, but a minus. Sorry for that. Sometimes mistakes happen, especially if you're doing something kind of off the cuff and in a live hangout. Now, if for whatever reason you don't really trust me with talking about pressure and all of that, and granted, sometimes it isn't that easy to understand, there's also another way that you can look at that problem, which is a little bit quicker to explain, and the math behind it is a little less easy. So, new page of paper. and again, our bucket of water, the surface of the water, and our object in here. Now, if you want to move that object down to, let's say, here, then basically there's already going to be water there at the place where you're going to move your object to. So that water has to go somewhere. So as you push down your object, you're going to displace the water. And now, at the point where your object was before, it isn't anymore. So that space has to be taken up by something. And for water and basically any other liquid that you can imagine, the water that you displaced from down here has to go up here. Now, again, the mass of our object is MO is going to be the mass of our object. And I'm going to use MW as the mass of the water that you displace. Yeah. Sorry for that clunky writing. I'm not going to study the art of writing beautifully, but yeah, never mind. Now, as potential energy is defined as, hold on. Yeah, I'm going to explain it that way. Now, potential energy is defined as the integral over the force needed to push an object along a certain path. Now, if we want to the energy of our object inside the gravitational field is going to be the height of our object times its mass times the gravitational constant. And the energy of the water that we displace is going to be the height the height of the water times the mass of the water times the gravitational constant. In that sense, you can think about it in the same as if you had both your object and the water that it is displacing on two trays of a really old scale, where basically you would put your reference weights in one tray and what you want to weigh in the other tray, and then see how many weights you need to basically make both of them match. As your object goes down, the water that it displaces has to go up. So the change in potential energy of our object is the change of height times the mass of our object times the gravitational constant, and the change of energy of the water is the height at which we have to move the water, which is going to be the same height as our object, times the mass of the water times gravity. So the total change of energy is going to be the total change of height times the gravitational constant times the difference in masses between the water and the object. Now, energy is defined as a force applied over a certain distance, and in that case, a height. So, if we rearrange that, we arrive at the force being our force being an energy that we require to move something for a certain height divided by the height. In that case, the total force that we measure our object pushing downwards equals this energy divided by delta H, because delta H is the height at which over which we move our objects, which is the gravitational constant times the difference in masses between the water and our object. which again is, which if we multiply it out, is, hold on. The difference is gravitational constant. Let me think about it one moment. In that case, it would probably make sense to divide to subtract the mass of the water from the mass of our object, because in that example we used a stone which was heavier than our object. So we turn these around and also turn these around. So in the end, we arrive at gravitational constant times mass of our object minus gravitational constant times mass of the water which it displaces, which is the same result that we got from our calculation when we did it with pressure, just getting there in a different way. Yeah. Basically, that's what I was doing my best at explaining in the Hangout that I was invited to. Now, granted, that Hangout was very chaotic. And in part, that is also my fault, because I went in there assuming that I just had two people who didn't understand something properly or had just a few questions. And basically, we were looking for a way to get an answer. And that probably was a mistake. Because what ended up in the Hangout was I would start to explain something, then a question would come up about a certain detail of what I was about to explain, and in the end, that would lead the entire conversation down a path focusing more and more at one detail, and in the process also moving the goalpost of what I was supposed to explain. Which is why at the end of the Hangout, everyone was talking about unless you can prove to me right here and now that gravity is real, all your explanations are invalid. And in regards to proving gravity, I'm going to do that one another time. I've made a video from a Cavendish pendulum that I recorded, and afterwards I had to notice that the video was utter crap and not really that well presentable or usable. So I'm going to repeat that experiment, and then on the next Hangout, or I don't know, someone just publish everything. However, back to that one. And also back to the reason for this entire Hangout. And to be honest, I'm pissed. I'm really pissed. Because nobody likes being called a liar. And I have to agree, the Hangout wasn't really that useful for explaining things, because, well, it was very chaotic, and I'm not really good at making chaos like that go away. But then again, I did explain, although be it constantly being interrupted and getting sidetracked and basically getting lost in chaos, what I was also explaining just now. And basically in your video, Anthony, you said that what I said made no sense, and to be honest, it does make sense. It involves math. I know you don't believe in math, but that doesn't really change that math works and can be used to prove stuff. And honestly noted, I did not lie to you. Seriously. I explained what I was asked to explain. I explained how gravity ties into all of that, with the gravitational constant, which takes into account the mass of the Earth and the height above the Earth, and the galactic constant, the uppercase G. That's where gravity comes into play with all of those explanations. So that point had been addressed, and the weight of the rock is also there all the time in my calculations as this part of the total of the formula. Those were the 2 points that you made in your video, claiming that I didn't address them, and I did address them. So, granted, until now, you didn't look to me like the kind of person who would intentionally missed that. So I'm ready to give you the benefit of the doubt that it just got lost in all the chaos of the Hangout. So I'm not really angry at you personally for that. And as I said, I'm not holding a grudge against you personally. But still, in that case, you were wrong and you missed it. And I'm again noticing that I'm about to turn this into a rant, which I really didn't want to do.
So, Hector, thank you very much for the explanation. One thing I'd like to go through is, you know that many flat earthers claim that there's no such thing as gravity, and
yes, I already came across that.
Yeah, and that the only thing that really matters is the density of the objects. Now, in your calculations, on both pages, obviously, you can clearly see that the factor g, which describes the gravitational acceleration of objects on the surface of the planet, clearly is relevant in every single of your equations.
Yep.
That being said, if any flat earthers are watching, or Anthony, if you'll be watching this maybe later, come up with an explanation that does not contain any factor that describes an acceleration downwards, because that is really the important thing that you really don't want to or simply can't address. At least I've never seen it. So if you find an alternative explanation, I'd really gladly see this.
Because basically all that gravity, basically the thing that gravity does is make things want to go down, and the way that gravity does that is according to that formula, which you can simplify on Earth into this kind of formula with g times m, with g being the gravitational acceleration on Earth, which is just a short version of that factor. And thing isn't the case. How else would you make all this work? If I understood you correctly.
Yeah, that's basically the question that I'd like to get answered from Anthony, or any flat earther for that matter, is how can you get rid of a constant acceleration downwards in any mathematical model? Because I don't see any way that describes how objects behave, at least on the surface of the planet. Yeah, that does not contain that factor. Because as you've shown in the beginning, the factor little g is nothing more than a simplification of the gravitational law. It's basically just the big G times the mass of the Earth divided by the radius of the planet squared. That's it.
Yeah. Because basically the mass of the Earth is very large, the radius of the Earth is very large. That constant is very small, and if you were to type those in every single time into your calculator, or simply carry those on through the whole equation, everything in here, where every little g is, I would have to write down this here, and that would only make it more confusing than it probably already is to people who aren't used to that.
Yeah, that's one of the points. Another point that I'd like to make. Anthony, or any flat earther, if you're watching this, why do you think that the gravitational acceleration is different for different parts of the planet? There's like a 3 or 4%, no, 0.3 or 0.4% change between the acceleration that you feel on the poles and the acceleration that you feel at the equator. I'd really like to see that explained from your side.
Yeah.
Because I've never heard it addressed at all.
Yeah. In terms of the gravitation, in terms of talking about it in the sense of gravity, the Earth is not a perfect sphere. It's
not
a little bit
spheroid, because it's turning, and we have also the centrifugal force that only equates. The
centrifugal force basically drags the material of the Earth at the equator out just a slight little bit, which is enough to just moderately deform it. And if you remember correctly, I was pointing out that this factor doesn't really change a lot if we move up or down inside of our water bucket, because that's only 1 meter over of height that we're changing the 6.3 thousand kilometers of the Earth. However, when we're going to the equator, there's the deformation of the Earth is going to be a little bit larger. So the radius here is going to change slightly. In terms of describing this via gravity, that's how this small variation in local gravity is explained. Now, there's also now further than that, there's even smaller variations of gravity, which is mainly due to the fact that the Earth isn't really a perfect deformed sphere, but there's also mountains and valleys, and yeah, a lot more to it. But again, those variations are a lot smaller than what you see when you're going from the North Pole to the equator.
Yeah, that's correct. So I'd actually like to open this Hangout now if you don't have anything to add.
To be honest, I was hoping to not open up this Hangout because I've got just a slight hunch that it is going to end up as, and I really like the chaotic nature of such shouting matches because as a result you get something like that from the last Hangout I was in.
I don't think that it will be a shouting Hangout because I don't see any flat earthers in the chat. Will be more like a random clusterfuck, but no real opposition, to be honest, at least today.
Yeah, but on the other hand, I also wouldn't really mind a little bit of opposition. So, and probably not really not even opposition, but just if somebody's got a question and you aren't going to plan this on doing another video that is probably by accident accidentally misrepresenting me, then I'd say you're welcome in here, and I'm happy to answer your questions.
So, does maybe anyone want to join or ask Hector a specific question about the topic that we've discussed today, or mainly he has discussed today? I'm talking to the chat, obviously. And not any troll questions, obviously, like Imric. We know you are no flat earther. Nobody. Okay, then I think we'll wrap this up for today. One thing I'd like to say is that you guys, I hope you're looking forward to our next experiment, which will be the Foucault pendulum. Unfortunately, we still don't have any date for it because the location we've chosen isn't really available all the time. So yeah, that might take some time. And obviously my stratosphere balloon, which will be launched in hopefully about 3 or 4 weeks. So thank you very much for, and see you later.